Okay. Okay, chapter 13, classroom discussion. Here we go with some practice on the ideal gas law and a little bit of a chemistry for our physics class. So, how many atoms are there in a 3.4 gram copper coin? So, how many atoms? That's definitely your Avogadro's number connection. And you have the normal mass in grams, not kilograms. And yeah, oh, here it is. The number of atoms is found by dividing the mass of the substance by the mass of a single atom. It's like one ice cream costs a certain amount, and then you have this much money. How many ice creams can you buy if the price for one is given? So you divide the amount of money by the price of one ice cream. Let's take a look at the periodic table of elements and see what we can get from it. That's the copper element. It's number 29. And see, there is this magic number beneath the name. It's 623.546. This is your atomic mass. And that's in those U's. U instead of a kilogram. So what it says is that copper has 63.5 U's in one atom. So one atom has the atomic mass of 63.55 units. Let's not forget that we have to convert to System International. This is your conversion factor between the U and the kilogram. So if it's 63.55 U's, then you can convert to kilograms and get the, whatever that is, 10549 times 10 to the negative 25th. See how U's cancel, right? Kilograms go on top, U's go to the bottom because you want to get rid of U's and be left with kilograms per atom. So this is the actual mass of one atom of copper. Well, that's it. Nothing else here. So moving on to the number of atoms. Remember, it's the not the Avogadro's number yet. Oh, you don't even need the Avogadro's because you already have the mass given. Yeah. See how it's 3.4 grams in the coin that we're talking about. So the total mass, here it is, that's given, 3.4 grams. And the mass of one atom, we just figured it out from the previous calculations. So it's kilograms. And if you divide by kilogram per one atom, division is multiplication by the reciprocal. So kilograms will cancel and you'll be left with number of atoms. That's literally what we just described. This is the money that you have in hand. This is the price of one ice cream. How many ice creams can you buy? You just divide the money, say $5, and ice cream costs $1. How many ice creams? It's 5 divided by 1, and you get 5 ice creams. So this is the number of atoms in that coin because we figured out the conversion factor between the U's and grams, and then, kilograms, and then you convert everything to those kilograms, and kilograms cancel, you're left with number of atoms. Oh, this is actually comparable to the number of all grains of sand on Earth's beaches, or the number of stars in the whole universe. This is a pretty large number. It's 3 times 10 times 10 times 10 times 10, and it's 22 times. You have to multiply by 10. So it's 3 and 22 zeros after it. So it's quite a number to consider just for a small coin, like one penny. The 3 grams would be like 1 cent coin. That's how many atoms and of copper it is made of. It's just crazy micro world. Okay, what is the temperature that you have to heat a brass rod for it to be 1.5% longer than it is at 25 degrees Celsius? 25 degrees Celsius is what you would normally call the room temperature. It's actually 20, but if it's 25, it's still close to the room temperature, just for your reference. This is the formula that we got from lectures. It's your elongation. It's one-dimensional change. It's not volume. It's just in a single dimension. Alpha is the coefficient of linear expansion that you borrow from the table. L sub 0 is the initial length. And delta T is the change in temperature. That's exactly what we want to solve for. How much of a change in temperature do we need to elongate something for, like, it's not something, it's actually brass. Brass is a certain material. And make it 1.5% longer. So solve this for delta T because temperature is unknown for this problem. So you divide both sides by alpha L sub 0, and you get this notation. And delta means what? Final, take away, initial. Okay, delta, it's final, take away, initial. That's the definition for any delta. So that's where we are so far. Yeah, and the question is not the temperature difference, but rather what's the final temperature. We have the initial temperature at 25 Celsius, and we want to solve for the temperature that we have to be at. So T is the unknown, not the delta T, but T by itself. So transferring T sub 0 to the other side, so add T sub 0 to both sides. That's what you're going to get. And here you have to be careful because we're not doing Celsius. You have to convert to Kelvin. And that's exactly how you do it. You have to add 273 degrees. You don't have to do 0.15. Remember how it was just 100,000 pascals for atmospheric pressure? You don't have to do 0.15 here. You can just do 273 and ignore the 0.15. It's fine. I'll give you full credit here. So 25 degrees Celsius plus 273, that's going to be the temperature in Kelvin. And the elongation is 1.5%. What is 1.5% in terms of a fraction? Because we can't do percent. Alpha is a number, L sub 0 is a number, so you can't do percent over a number. You have to stick to numbers. The increase of 1.5%, well, that is a change, because delta is a change of 0.015. Because if you multiply it by 100, you'll get 1.5%. So this is your 1.5% increase. And alpha is coming from the table for brass. And you have your 1,000 and what? And 100 degrees Kelvin. So you have to heat up this piece of metal pretty badly. Metals do not, change their form easily. You have to really heat it up to a substantial temperature. That's what it says. I mean, it makes sense, even though it's 1,000 degrees, but those are Kelvin, not Celsius, and it actually makes sense for a metal, for a piece of metal. That's what you get for the temperature. Be careful, it's all Kelvin. Temperature is in Kelvin, and pressure is in pascals, and volume is in meters cubed. Okay, on to the ideal gas law. We got a scuba tank with air, and the gauge pressure is 204 atmospheres. Be careful, we can do atmospheres. We have to convert to pascals. And the air temperature is 25 Celsius. Be careful, you can do Celsius, you have to do Kelvin. And diver jumps into the ocean. And after a short time, tank's pressure is 191 atmospheres. So, yeah, diver has inhaled some of the air, but it was not so much. of a change, so you can ignore that change. And what's the temperature of the ocean water? So see how it's easy to say how hot is the ocean just by looking at the change in pressure in a scuba tank that you charge with air on the surface. And then once you dive into, you can tell how hot or cold the water is. So what are we going to do? We're going to do the ideal gas law: pressure times volume on one side, concentration, gas constant, and temperature on the other side. And the mass is in kilograms. Mu is what you get from the periodic table of elements. And if the gas is the same, which it is the same, and mass doesn't change, the amount of gas does not change. And yeah, even though diver inhales something, but it says negligible amount here, so you don't have to consider any change in mass. You can consider this ratio to be constant. And don't forget that R is also called constant. That means it doesn't change. So you're technically just doing the ratio between the P1V1 to P2V2. And on the other side, it's going to be the ratio of temperatures, but of course in degrees of Kelvin. So mass is unchanged. The gas is the same air, so mu1 is mu2. And volume of air is the same. It's the same scuba tank. It was scuba tank of a certain volume. Once you dive into water, it's still the same scuba tank with the same volume. So volume is the same. And same chemical content for air. So what you will be normally doing in terms of algebra is you'll be dividing the equations left side to left side, right side to right side, and this is what you're going to get in this case. So everything cancels, V cancels, M1 to mu1, M2 mu2 cancels, and gas constant R also cancels. So it's just P1 to P2, T1 to T2. And it's easy to solve with cross multiplication or any other method that you can think of. I'm doing cross multiplication here. If you want to know about the ocean, so you want the second condition, not the first one. The first one is for the surface at the 29 degrees Celsius. You want the ocean. So here we go, cross multiplication. Be careful, you have to convert to Kelvin. It's not 29, it's 29 plus 273 degrees for the Kelvin scale. So ratio for pressures, 10 to the fifth, 10 to the fifth cancels out, and it's just 191 divided by 204. Whatever's the ratio multiplied by the, what is it, 300 and like 300 and what is it, 29. So yeah, just 300 plus a little bit of a change for Kelvin, and you're going to get 280 degrees Kelvin. This is how hot the ocean is. Well, it's 273 for the conversion factor and 29. So it was like 300 and what, 2 degrees. Now it's 280. So yeah, there's quite a difference between ocean water and the air on the surface. So it's less, right? It also makes sense because it's less, because ocean is a little cooler than the surface, the seaside. And be careful, everything is in Kelvin. So do not panic with 280 degrees value. Yeah, that's what it is for the ocean in terms of Kelvin. No more Fahrenheit, no Celsius, only the Kelvin scale. Okay, some more practice with ideal gas law. We got a certain volume in liters, C61 liters of oxygen at a certain temperature, and that's in Celsius, which is also not good. We have to convert to Kelvin. And absolute pressure is in atmospheres. See, I'm giving you all the bad units, so you have to convert everything to System International first. And then it is compressed to 38 liters And at the same time, temperature is raised to 56 degrees. What's the new pressure? See how it's the volume, liters, the temperature, and pressure that are connected. They're all connected. So change in one parameter would produce changes in other parameters. So for all of those changes, we have the ideal gas law. And once again, this is your first condition. This is the second condition. And in here, mass is still unchanged. You have all sorts of compression, heating, but it's the same amount of gas that is in the system. So you say masses are the same, and it's the same air before and after. You didn't add any, I don't know, argon or, I don't know, neon, any other gases that you can think of. None of that was added. It's still air. So the ratio m to mu is constant. And if you'll divide the top equation by the bottom, this just cancels. Whatever's the ratio, it's the same ratio for the conditions before and after. Also, R will cancel because it's gas constant. It's the same value, so divide top by the bottom. R cancels. But this time, nothing else cancels. You have, see how it was P to P, T to T. Now, you can't say the volume is the same. The volume has changed as well. So it's not just P to P, T to T. You have the combo, pressure and volume, and pressure and the volume that you have to treat as a combo, like the whole thing together. So I want to point out that pressure and volume is still proportional to temperature, which is the ideal gas law idea. So it's just a little more complicated this time because you have to take care of pressure and the volume and the temperature. It's still the cross multiplication that I like to solve here because we have two fractions, top over the bottom, top over the bottom. So you just cross multiply. That's what you get from algebra. And it's a little more calculations. And it's mostly conversions rather than calculations themselves, because if it's pressure, it must be in pascals. And it's given as what? 245 atmospheres. So this time it's 2.45 times 10 to the power of 5, because one atmosphere is 100,000 pascals. Volume. Volume is in liters, which is not good, and you have to connect it to meters cubed. Meters cubed are the U-System International. So it's your 61 liters, and see how it's thousands of a meter cubed. So you multiply by 10 to the negative third, and that makes it meter cubed. You might argue that, hey, it's 10 to the third here, 10 to the third at the bottom, that cancels. Why do we even bother converting? The answer is you should always use System International. Even if it cancels top and the bottom, you still want to show your work as conversion to System International in physics. Please do so. So liters here, liters there, you convert them both to meters cubed. And now the temperature. That's the trick part here. Remember I said, hey, if it's delta T, you're going to get delta here, delta there, so 273 will disappear. Not in this case, though, because if it's just temperature by itself, you'll get, what is it, 320, like 29. And in here, it's 200 and what, 70, like 80, 91. If you add 273 to convert to Kelvin, to both numbers, it's not going to be the same as 56 to 18. Check it out. Divide 56 by 18, or divide 320 versus 291. You will see that the ratios are different. So conversion to Kelvin is very important here. And once again, I cannot stress enough for the whole chapter in thermodynamics in general how important it is to keep track of units and convert to System International. All of your mistakes will come from not converting to System International. So grab your calculators once we're done with our discussion and make sure you're getting the same value on your calculator. And if it's pressure, it must be in pascals. So it's 400,000 and 39,000 pascals. That's the new pressure after you increase the temperature and compress the volume, which makes sense. Volume is less, pressure is more. And if you heat it up, remember the Charles law, the more the temperature, the more the pressure, so definitely an increase in pressure. If pressure was 2.45, now you get 4.39, so the pressure is doubled. Makes sense. That's what you would expect. You would expect pressure to be more. And once again, the key is the ideal gas law. Before and after something happened, just see what's changing and see what's kept constant. And if it's constant, you just cancel it and you get the way you solve algebra, most likely cross multiplication. But if you have some other ideas, okay, go ahead. It's really up to you on what you're going to do here. Okay, another fun story. Estimate the number of moles and molecules of water in all the Earth's oceans. Consider 75% of the Earth to be covered with water to an average depth of 3 kilometers. Well, that's actually a real world numbers. On average, that's what you get. So let's count all of those molecules. Yeah, the radius of Earth is 6,400 kilometers. So ocean volume is really close to be a sphere, a spherical shell with a certain surface area. Surface area is 4 pi r squared. R is the radius of Earth. If you'll subtract 3 kilometers, fine. You can go with 6,397. Not going to change much. I'm going to go with 6,400 anyways. And thickness delta Y. Thickness is the 3 kilometers. So we have all the parameters here. Density of seawater. Remember, it's 1,000. For all the water that you think of, you just say 1,000 kilograms per meters cubed. And for moles, we're going to go with definition of a mole. So first of all, it's the volume. How much water in terms of volume do we have to consider? It's 75%, so it's 0.75 coefficient in front. The surface area is 4 pi r squared, r being the radius of Earth. And your thickness is the depth of 3 kilometers that is given as well. So 75% for, and then you have the pi, the ratio between the circumference and the diameter. And the radius of Earth goes squared. That's quite a number. But it's even a greater number if you multiply it by 3 kilometers. Kilo means you multiply by 1,000. Kilo is 1,000, so it's 10 to the power of 3. So if you'll grab your calculators and double check the work, you'll see that the overall volume of water on planet Earth is about 1 times 10 to the 18th, so 18 zeros after number 1, meters cubed. So it's good that we already have System International units. So next is your definition of density, which is mass over volume. So calculating for mass, it's the volume times the density. Density is 1,000. Yeah, I say 1,025, but if you just show 1,000, it's fine. Like I said, 1,000 for water, kilograms per meters cubed. That's what is expected. And volume, it's just what we figured out from the previous calculations. So we get the volume, we get the density. You can calculate the mass. And this is the total mass of water on planet Earth. That answers part 1. Oh, no, it's moles and molecules. Never mind. We're almost there with mass. Moving on to the definition for water and what the moles are. For that, we need the atomic mass of water, H2O, in case you didn't know the chemical formula for water. Hydrogen has roughly one. It's I'm super specific here just to show you what kind of number I'm talking about here. And it's H2. So you multiply this atomic mass by 2 for 2 atoms. And 1 atom of oxygen, which is really close to 16, but for super duper accuracy, we keep it as 15.999. Multiply by 1, add together for the total H2O formula, and you get 18 grams per 1 mole. Of course, we don't want grams, we want to convert to kilograms because we know the total mass of water in kilograms from the previous calculations. So now, once you convert it to kilograms per mole, see it was 18 grams per mole, now it's 1,000 times less because we're talking kilograms per mole. So total number of money is this much. One ice cream costs this much. How many ice creams can we buy? Well, you divide the amount of money by the price of one ice cream, and you get this many ice creams, this many moles of water that we have here on Earth. That means 7 multiplied by 10, 22 times. And for number of molecules, we need the Avogadro's number because it is literally the number of molecules in 1 mole. So if you have this many moles, and you know the conversion factor between the number of molecules to 1 mole, you put mole at the bottom, so moles cancel, and you're left with number of molecules. So you multiply the total number of moles times the molecule per 1 mole, and you're left with number of molecules as a crazy 10 to the power of 46. That means 4 and 46 zeros after that. That's the number of molecules of water that we have here on Earth. So this problem, combined with previous analysis of copper, like this one, should give you an idea how chemistry is really connected to physics. The reason I'm giving you this number 2 and the number problem number 2 and problem number 40 is because I want you to see how science really connects everything. And sometimes you don't see that connection, and boom, with basic definitions from chemistry and a little bit of physics, you can do some crazy calculations and end up with cool scientific facts for your, say, research. Say you want to know how much water is evaporated because of the heating from the sun, or you want to know the I don't know, thickness of a cloud or whatever, you will still need the total mass and the water content in the first place. And you can definitely borrow this knowledge from a physics class combined with sorry, headset turned off. Combined with chemistry class and physics class, you can do a lot of crazy calculations. This is one of the examples where you really benefit from getting, pretty cool number of molecules of water on all planet Earth. Oh, and we actually have one more practice with chemical elements. This time it is how fast helium atoms actually move near the surface of the sun. The temperature of the surface is about 6,000 degrees Kelvin. And helium is number 2 in periodic table of elements, and it has atomic mass of 4 units. So let's use this knowledge to figure out the RMS speed, the root mean square speed. From lecture notes, we derived the formula for kinetic energy, which is 3/2 of a cat. And now we solve for the speed. And it's not even squared anymore. That's why it's root mean square. K is the Boltzmann's constant. That's the value, in case you didn't know. And temperature in here must be in degrees Kelvin, of course. You have to convert temperature to Kelvin, which is already here in Kelvin. You don't have to do conversions. But if it's Celsius or Fahrenheit, make sure you convert to Kelvin. So this is our conversion factor from the past. It converts U's to kilograms. We need that because all we have for helium is just U's, U per atom, and we need kilograms for our calculations. The mass of a single helium atom is therefore 4 times the conversion factor, and you get this many kilograms per one atom. That's only one atom. And now it's 3 times the Boltzmann's constant times the temperature in Kelvin divided by the mass of one atom. That's what we just got here. And boom, it's actually 6,000 meters per second, which is like 13,000 miles per hour. Those atoms and molecules move pretty fast because the temperature is what? 6,000 degrees. Temperature tells you how fast everything moves, and we have some crazy motion at 6,000 degrees Kelvin. Yeah, that's the root mean square practice. And once again, you can borrow some data from periodic table of elements, convert it to kilograms, and do some useful calculations because you have this mass entering a lot of formulas in science. Now, how about a root mean squared of oxygen molecule at 0 degrees Celsius? And how many times would it move back and forth across like a classroom on average, assuming no collisions with other molecules? So pretty much, how fast will the air move in a classroom at, it's not, you can't call it room temperature because 0 Celsius is like freezing for water. It's like somewhat cold, but it's not far from room temperature. So you can still think about like how fast would your air molecules move in your room that you're sitting at right now. So oxygen has two atoms, and you borrow 15.999, multiply by 2, you'll still get 32, like 16 times 2, 32 grams per mole. This is your atomic mass. And it's the root mean squared. That's for how fast it will move, but you have to do some conversions. The Boltzmann's constant, the constant 3, is still there. And then there's temperature. Temperature is 0 degrees Celsius. 0 degrees Celsius, you have to convert to Kelvin, which is 273 Kelvin. So this is your temperature. And for the mass, you go with the grams per mole, convert to kilograms, and then use the conversion from U's to kilograms. So what you have here is molar mass multiplied by the conversion factor, and the molar mass in kilograms. So you have to do the overall conversion to kilograms. So 461 meters per second, this is your root mean square for molecules of air. Check this out. It's like 1,000 miles per hour that all the atoms of air move back and forth in your room, and you can't see any of those motion. If you'll do the average statistical analysis for XYZ direction, you can use this trick with division by radical 3 to get the actual velocity, and time between collisions from side to side would be distance over the speed, because time is distance over speed anyways. And for the round trip, you double the distance. And if you want the frequency, it's the inverse of a period. So if this is for one complete round trip, the inverse of that number is the frequency of how many times per 1 second you do something. And you get about 27 times. Just imagine 27 round trips per 1 second for all the air molecules that you see right now in your room. Everything moves crazy fast, even at normal temperatures, even if it's not the sun. Remember, for the sun, it was 6,000 degrees, 6,000 meters per second, which is crazy fast. But even at normal room temperature, we still have 400 meters per second, which is approximately 1,000 miles per hour. Everything moves around you so fast you can't even recognize it. You can't see any of that motion, and yet it's happening right now in your room. So molecular kinetic theory really opens up some cool perspective on micro world, and we use just basic physics formulas combined with a little bit of chemistry. So the stuff that you're going to use is found below the element symbol, the atomic mass, and you got to know though for which gas you have 2 atoms and for which you have only one atom. Still, quite an estimate to work with. Chemistry is a lot of fun, well, especially when you combine it with physics. So 27 times back and forth in 1 second, okay? 1 second, you count 1 Mississippi, 2 Mississippi, boom, it's already 54 distances traveled by a single air molecule. I keep on saying air, not oxygen, because air is made of nitrogen and oxygen. And for nitrogen and oxygen, you can think quite similar atomic mass units. Oh, and that was it. That was the last slide for this chapter. Let me stop the recording.